The dimension of a vector space is the number that sort of sits at the sweet spot between having enough vectors to talk about everything in this space and not having too many. And so we'll look at a theorem or two that describes this. So first off, any spanning set for a vector space contains a basis, and any linearly independent subset is contained in a basis. Okay, so let's look at these two sort of inside out and twin ideas. So if we look at the reason why these are true, so for the proof of the first one, suppose, I guess for both of them, suppose that we've got some set S that looks like this. Okay, so if S spans V, and so let's see, so oops, I was looking at the wrong one. Okay, so let's look at the reasons why these are true. So for the first one, we're going to start with a spanning set. So let S be a spanning set for V. So in other words, the span of S is V. Okay. So let's see, if S is linearly independent, then it is a basis. If S is not independent, then one of its elements can be written as a linear combination of the others. Okay, so then remove it. So let S1 be S minus, like pull out, whichever one can be written as a linear combination of the others. Okay, and then rinse and repeat. So if S1 is independent, then it is a basis. If not, it has some element which is a linear combination of the others, because that's what it means to be linearly dependent. And so you just continue doing that. So just say, okay, have we gotten rid of all the redundancy? If the answer is no, then find a redundancy and throw it out. How about now? How about now? How about now? Just keep doing it. After repeating some number of times, you'll arrive at a basis, because we started with a finite spanning set. Okay. Let's see. So now let's look at the other one. So now suppose we have a linearly independent set. Okay. And I should mention, by the way, that these proofs that I'm giving you for both cases, this is for when the vector space is finite dimensional. Vector spaces of functions are infinite dimensional. Vector spaces of like Rn and matrix spaces and stuff like that, those are finite dimensional. So I don't want to get into the technicalities too much, but just throwing that out there. You need to do more work, and it's outside the scope of the class to talk about the infinite dimensional ones in any kind of technically rigorous way. So, okay, so suppose we've got a linearly independent set S. So then, let's see, if S spans V, then S is a basis. If it doesn't span V, then there's some new guy, let's call him VK plus 1, so he's not on our list yet. And he is not in the span of S, right? So if the span of S is not all of V, then there's something that's not in it. Take that thing that's not in it, call it VK plus 1. And then we just add it. So for sets, it's called union. So, so we say let S1 be S union our new guy. So we throw in VK plus 1. And again, rinse and repeat. So if the span of S1 is equal to V, S1 is a basis. If not, look for another thing that's not in the span and keep on going. Eventually, you get a basis. And that's as close as we're going to get to a proof for this theorem. So the idea here, the significance or the meaning of basis is so I'm going to use this symbol, absolute value of a set, the magnitude of a set. That's supposed to be the size of a set. So this is my symbol for the number of elements in the set S. Sometimes it's called cardinality. So it's the cardinality of S. Okay. So the significance of the dimension is that if the size of S is strictly smaller than dim V, then it cannot be a spanning set. It doesn't have enough stuff. If the size of S is strictly greater than the dimension of V, then S cannot be linearly independent. So the only way that you can have a set which is spanning and linearly independent at the both at the same time is when you have the number of things equal to the dimension. Now, if the dimension is 6 and you have a set of 6 things, then that definitely doesn't mean you have a basis, because, I mean, maybe you just have like 6 scalar multiples of the same object, then it definitely wouldn't work, right? But in order for it to be possible that it's a basis, then it has to have the dimension number of things, or it's not going to work. So in general, the sort of setup is like this. So if you have a basis, then any subset of it is going to be linearly independent, and any set that contains it is going to be a spanning set for for V. So for instance, suppose you have a basis and it looks like V1, V2, V3 up to Vk. Okay, then if I take V1 and V2 and V3, this is guaranteed to be linearly independent. If I take V1, V2, V3 up to Vk, and then I throw in something that's not in that list, then this is still going to be a spanning set. Now, actually here, let me use the restriction. I throw in something else. Okay, it will still be a spanning set. Now, it's no longer going to be a basis though, because I know that Vk was in the span of V1 through Vk, and that means that it's redundant, so it's not going to be linearly independent. And similarly back here, when when I took this subset right here, I know that that is not going to be a basis because it is too small to be spanning, because it doesn't have Vk, for example. So one way of thinking about dimension is the definition, which that it is the number of elements in a basis. The other way of thinking about dimension is that it is the number of free parameters or coordinates that you need to specify something in terms of that set. Because if we look at this basis that we had just right here, and we say, okay, so then I know that any given vector can be written as C1 V1 plus blah 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 up to CK Vk. One way to look at this is to say, hey, there are k basis vectors. So the dimension is k. Another way of looking at this is to say, oh, there are k free parameters, or k coordinates. In other words, in order to specify where U is in this vector space, I have to tell you k pieces of information. It's first coordinate, second coordinate, third coordinate, etc., up to kth coordinate in terms of this basis. And both of those are equivalent ways of understanding that the dimension has to be equal to k. And so, in conclusion, we can say that the following are equivalent. It's been a while since I've written this, so I'll just rewrite it here. The following are equivalent. B is a basis for the vector space V. B is a maximally independent set. And B is a minimal spanning set. And so in case it's not clear what these terms mean, so just to be precise, maximally independent, that means that B is independent, But if I add anything else in, so if I throw in some other vector u, so if I take some u that's not already an element of B, and I throw it in, then I get a resulting set which is no longer independent. And minimal spanning set, that means that B is a spanning set, but if I take anything out, so if I take some element u from B and I remove it, then I get something that's no longer spanning.